Well, hello there, everyone. I have a little bit of a demonstration to show you. Here I have what we call a Geiger counter, and I'll go ahead and get it turned on. We'll stop it, we'll reset it. Okay, here we go. Now you can see right now the numbers say 0, 0, 0. Now what a Geiger counter does is the whole purpose of a Geiger counter is to count how many little radioactive particles hit the detector. So you can see right here is where the detector is. It says detector on there, so that's how you know. What you can do is you can slide out one of these little guys and you can put a little radioactive material in here, slide it back in, and then the Geiger counter will start counting. And it'll start counting how many little radioactive particles hit the detector. Now, right now, if I hit the count button, it'll start counting, and you'll see that I have nothing on this tray. But if I go ahead and start counting, then you'll see that it is counting the little particles that are hitting this thing. Now, there are particles that are hitting this thing right now because of background radiation in the room. Turns out that radioactive particles are everywhere, and so every time you breathe, you're breathing out radioactive particles. Every time you breathe in, you're breathing in radioactive particles. Carbon-14 is all around us, and carbon-14 is radioactive. So you'll see that there is some amount of radiation here, even though there is nothing here to be detected. That is what we call background radiation. Now I'll go ahead and stop this here, and we'll reset it. And now I'm going to get an actual radioactive sample here, right here. These are my radioactive samples. So what I'm going to do is I'm going to take out a little beta sample. Now this sample right here is actually emitting radioactive, or it's actually radioactive right now. When I slide it in here, you'll be able to see that. I'll go ahead and hit count like this. And you can see that those numbers start ticking up at a much faster rate than when there was only background radiation. That shows that right now this thing has counted 28 particles that have come from that thing, and the number is ever increasing. That's my little beta radiator, my little beta emitter. Now let me turn it out for something else. I'm going to take out my little beta emitter here, and I'm going to put in instead a little gamma emitter. Here's my little gamma. I'll go ahead and stop the count. We'll reset it. Plug in my gamma, and you can see that when I hit the go button, it counts even faster. Now you could imagine that you could talk about how many counts on this thing come up per second, and that would be a totally fine way to measure radioactivity. If you're getting more counts per second, then you have something that is more radioactive. If you're getting less counts per second, then you're getting something that is less radioactive. Here you can see my gamma radiator is way more radioactive. Let's go ahead and stop that, little buddy. We'll reset it here, and I'm going to trade this out for my alpha emitter. Here's my alpha emitter right here. We'll go ahead and slide it in. Go ahead and hit the start button. You got it. And there it goes. Very, very slow. You can see that my alpha emitter, is not quite as radioactive as either of the other two. It's just simply not putting out as many particles per second. In order to talk about how strong of a radiator something is, we often talk in terms of counts per second. And we have talked about counts per second so many times that we actually give this a new unit. And the unit that we give it is becquerels. I'll show you right here. I'm going to go ahead and stop this, reset it. Let's take out my little alpha emitter here, and we'll get that put away. Okay, slide this back in. Turn this around like this, and we're going to bring it up here. And I'm going to show you something on the whiteboard here. Wait. Okay, perfect. Ah, I dropped a pen. Okay, try again. We often will talk about radioactivity and how strongly radioactive something is in terms of units that we call becquerels, where a becquerel is the number of counts that a Geiger counter counts per second. So you can see that we had way higher becquerels for my gamma than we did for my beta or for my alpha. Now here's a little tidbit of information that I want to share with you. I have 3 radiators, 3 emitters of radiation, an alpha emitter, a beta emitter, and a gamma emitter. My alpha emitter has a half half-life of 138 days. My beta emitter has a half-life. The half-life of my beta emitter is 28.6 years. And finally, the half-life of my gamma emitter is 5.27 years. Now, here's a question. You saw here that the one with the highest spectrals was gamma, the one with the second highest spectrals was beta, and the one with my third highest spectrals was my alpha emitter here. Now, what if I told you that the radioactivity of each of these had everything to do with their half-lives? You would say, that makes no sense, Miss Wilson. And you would say, that makes no sense because you said this one's 1, 2, and 3, and yet this one is the shortest, medium, longest. That makes no sense. Well, the truth is, how radioactive they are does have everything to do with their half-lives. But in order to understand why, you have to understand something about half-lives, which is our topic of the day. I'm going to go ahead and get us resituated here. So I'm going to pause the video and we'll come back in a moment. Here we go. Okay, great. We are all situated here. Now, today we are talking about half-life. Now, before we talk about half-life, I think it's important that you have a definition for half-life, and then we'll talk about how half-life actually impacts radioactivity. So let's start with a quick definition. Half-life is the amount of time it takes, yes, do write this down. Half-life is the amount of time it takes for half of a given sample of an element to change into another element. It's the amount of time it takes for half of a given sample of an element to change into another type of element. Say, for example, that I had here I'll blow this up a little bit so that you can see it. Say that, for example, I had here a rock of pure uranium. Now, if I had a rock of pure uranium here, that would be very bad because I'd be holding a rock of pure uranium in my hand, and I just would not advise that for anybody. But say here that I had a rock of pure uranium. If I had a rock of pure uranium, that uranium is not going to stay uranium for very long. If you look at our periodic table over here, okay, yes, it is. Everything is just going so nicely. If you look at our periodic table over here, uranium is probably not going to stay uranium very long. It's super radioactive because it has such a big nucleus. So it's going to alpha decay into thorium. And then that thorium isn't going to stay thorium very long. It's probably going to alpha decay into radium. And that radium isn't going to stay radium very long. In fact, it's probably going to alpha decay into radon, and then after that it'll become polonium, and eventually it'll probably become lead through a series of alpha and beta decays. That means that this rock of uranium is not going to stay uranium for a very long amount of time at all. In fact, it'll be uranium for a little bit, but then little atoms will slowly start to decay. The half-life, if this was a rock of uranium, is the amount of time that it would take for half of this rock to no longer be uranium. The other half will still be uranium. It obviously doesn't split like that, but half of it would still be uranium, and the other half would not be uranium. The half-life is the amount of time that it would take for that process to occur, for half of the rock to be uranium and half of the rock to not be uranium. Now, you can imagine that this would actually kind of have a sort of exponential effect, and let me describe what I mean. If it takes one half-life, and after one half-life, half of this rock is uranium and half of it is not uranium, then after another half-life, the half that was still uranium, now only half of that would be uranium. And then after another half-life, the half of the half that was still uranium will now get cut in half. So only half of that will be uranium. So now all that's left will be a half of a half of a half, or in other words, 1/8. So after one half-life, half of it is uranium. After two half-lives, a quarter of it is uranium. And after 3 half-lives, 1/8 of it is uranium, and for so on and so forth, until all of it eventually will no longer be uranium. That's the idea of a half-life. Now, when I first heard about half-lives in 8th grade, I thought this was a very confusing way of talking. I thought, why don't we just talk about, like, how long it takes for one uranium atom to decay? Like, why are we talking in terms of, like, half-lives? Or why don't we talk about how long it would take for the whole thing to decay and no longer be uranium? Wouldn't that make more sense? Like, instead we decided to talk about, like, let's talk about the amount of time it takes for 1/2 of that stuff to become no longer uranium. Instead of talking about, like, wait, let's talk about how long it would take for all of it. Like, doesn't that just seem more logical? Well, here's the reason why we talk in terms of half-lives, is because it's all about probability. If I took one little penny here, and I wanted to know how many times do I have to flip this penny before it comes up heads? Well, you would say, hard to say. You could say, Miss Wilson, it might take one time. And sometimes it does take one time. Oh, unless I totally lose the penny. And hey, it came up tails. So sometimes it doesn't take one time. Sometimes it takes 2 flips. Nope, still came up tails. Sometimes it takes 3 flips. Nope, still came up tails, actually. Sometimes it takes 4 flips. Still came up tails. I kid you not. I'm not even making this up. Okay, wait, try again. Try again. And now it came up heads. That time it took 5 flips for this thing to come up heads. The other 4 times it came up tails. And so if I asked you, how many times do you have to flip this thing in order for it to come up heads? You could say, well, it might come up the first time, or maybe the second time, or maybe the third time, or the fourth time, or the fifth time. Has to happen eventually, probably, but like, I don't know when that's going to happen. It's nearly impossible to predict how many times this thing is going to have to flip until it comes up heads, because on every flip I have an equal 50-50 shot. So it's really, really hard to talk about how many times this is going to come up heads, or how many flips until it comes up heads. But if I had 100 pennies like this, and I said, hey, I'm going to take 100 pennies, and I'm going to dump 100 pennies out onto the table, then how many of them are going to come up heads? You would say, well, that's a much simpler problem, Miss Wilson. And you would bet it's probably going to be about 50. And in this case, I could count them all, but that is probably not worth your time. In this case, yes, you would have about half of them coming up heads and about half of them coming up tails. Now this is much more predictable, and you are going to get in the 47, 50, 51, 52 range every single time. I did this little demonstration in class 4 times today, and every single time that I did it, I got within a range of 47 to 52. Every single time, I get about half the pennies that come up heads and half the pennies that come up tails. This is much more predictable, and it's the same thing with little atoms. If this was one little uranium atom, if I took one little uranium atom off my rock of uranium and I said, hey guys, how long do you think until this one little uranium atom is no longer uranium? Well, it could be 30 seconds. It could also be right now. It could also be in 30 years, or it could be in 30,000 years, or it could be in 30 million years. There's really no way of telling how long until that little uranium atom is no longer uranium. But if I had a whole rock, it is much easier to predict, hey, after a certain amount of time, how much will be left? Way easier to say, oh, half will be left after a certain amount of time. Same thing with the pennies. Very, very hard to predict how many flips until one penny comes up heads. Very easy to predict how many pennies will come up heads if I flip 100 of them. It's the same kind of idea. Now, we use half-lives to talk about radioactivity because of probability, because it's way probabilistically helpful to us to talk in terms of half-lives instead of talking about how long until one little uranium atom decays, because that is not something that we can predict. But how many will decay after a certain number of time, that is way easier for us to predict. Same thing with the pennies. Now, the pennies here actually serve as a great model, as a great analogy for exactly how radioactive decay works. Hang on, I gotta put all these away. These actually serve as a great model for how radioactive decay works. And I want to show you what I mean. Let's say that I took 100 pennies. Let's make a little graph here. Let's say that I took 100 pennies, and each time I flipped the ones that were heads. And then I flipped all the pennies, and I took out the ones that were heads. And I took out the ones that were heads, and I left just the ones that were tails. Well, this would be a really great analogy for us looking at something like uranium atoms. Now, here's the idea. Suppose, for this example, we'll make a little graph here. Suppose that the number of flips represents the number of half-lives. You can imagine that each time I fill the beaker and each time I flip all the pennies, that is kind of like the half-life of a little block of uranium. So we can write this as number of half-lives. So in our analogy here, flips are going to represent half-lives. And then on our y-axis, let's put the number of pennies that are still tails. We'll say this, suppose that every time I flip it, we can say that each little guy, each little penny here, is going to act like a little uranium atom. And let's say that when it flips and comes up heads, if it comes up heads, that means the uranium atom has decayed. If it comes up tails, that means that the uranium atom has not yet decayed. So, the number of pennies that is still tails kind of represents the uranium that is undecayed. Now this acts as a really nice analogy. At time t equals 0, I have 100 pennies that have still not come up heads yet because I still have all of them in the jar. But after just one flip, of the beaker, wait, I'll put a few lines on here. 2, 3, 4, go out, 5, 6, like this. Okay. After one flip of the beaker, now I'm going to have about 50 of the pennies will come up heads and about 50 will stay tails. So at first I start with 100% of them are heads, or 100% of them are there, they're all tails. But then after one flip, only 50 of them are now tails. Then after another flip, that'll probably split it in half again, and we'll get about 25. Because I'm only going to flip the ones that stayed tails. So after that, I only have about a quarter of them that come up tails. And after that, if I flip it again, if I take the remaining ones that are still alive, the ones that haven't become heads yet, and I flip those, well then I'll have probably around 12-ish. It'll be around 12 or 13-ish. And so then I'll have only this many. And then if I flip it again, well, I'll only probably have about 6 that survive. And then if I flip it again, I'll only probably have about 3 that survive. And if I flip it again, I'll only maybe have 1 that survives. And every single time that I do this demonstration in class, after about 7 flips, normally before we get to 7, around 6 or 7 flips, all the pennies come up heads, and there are no more that are still tails. If you look at this graph, you see here that we get a nice, whoa, nope, not like that, Miss Wilson, try again. We get a nice little path. Oh gosh, the first one was better. Oh, it's so embarrassing. We get a nice little path. This is going to be awkward because you should draw it as like a uniform line, but it's really hard for me to draw it as a uniform line when I'm using this little pen on the computer. We get a nice little path that looks like exponential decay. Exponential decay is really what happens when you have a little block of radioactive material that's decaying, because half of it will decay in one half-life, then the next half will decay in the next half-life, then the next half will decay in the next half-life, then the next half will decay in the next half-life. And because each time the amount of stuff that's left there to decay is getting smaller and smaller and smaller, well, it's going to look exponential, just like this curve. Hey, go ahead and try this practice problem. Suppose that I had some radium. Let's say that I had some radium-226. That's the most common isotope of radium. Let's say that I had some radium, and its atomic number is 88. And suppose that I had some radium in my hand here. Suppose I had 8 grams of radium in my hand, which would be very unwise, but suppose that I did it. The initial amount that I start with is going to be 8.0 grams. Now here's something that you should know about radium in order to do this problem, is you need to know that radium has a half-life of 1,620 years. Here's a question for you. If I held 8 grams of radium in my hand, after 4,860 years, when my hand is no longer looking so nice, how much radium will still be radium? And how much will it turn into another substance? Well, you could do this problem in your head. Go ahead and try it. Like for serious, pause the video, actually try this in your head. Could you do this problem in your head? Okay, here's what you said. You said, Miss Wilson, I'm seeing that 4,860 years, that's 3 half-lives. And if it's 3 half-lives, that means I'm going to cut it in half 3 times. So after the first half-life, at first I have 8 grams. It's like starting out with like 100% here. But then after 1 half-life, I'm down to 50%. I got to cut it in half. You cut it in half, and then you only have 4 grams. Then you have another half-life, and it gets cut in half again. And when it gets cut in half again, now I only have 2 grams left that are actually radium. The other 6 grams are now whatever it decayed into. And then after a third half-life, I have to cut that in half again. So now I only have 1 gram left. Here's the idea. Every time I experience a half-life, I cut it in half. So after 1 half-life, I have half. After 2 half-lives, I have a fourth. After 3 half-lives, I have an eighth. And so that means that after 3 half-lives, only half of it is remaining, or only an eighth of it is remaining. And I started out with 8 grams. Then after 3 half-lives, I will only have 1 gram. Now, you just did this in your head, but there's also a mathy way to do this. And actually, there are 2 mathy ways to do this. The first way that I shall show you, I shall call the McKellips way, because it comes from Mr. McKellips. And the second way that I shall show you shall be the Saxon way, because it comes from Mr. Saxon. So the Saxon way will be more familiar to you, but I'll show you the McKellips way first, because it is exactly what you just did in your head. Here's the McKellips way to solve this problem. The McKellips way to solve this problem goes like this. It says, okay, the first thing that I'm going to do is I'm going to figure out the number of half-lives that have passed. And I'm going to call that n. You should label this in your notes. Like, I would label this, if I were you, like number of half-lives. But I kind of run out of space here with my big old clunky marker. But I'm going to figure out the number of half-lives. Now, if I want to figure out the number of half-lives, this is exactly what you did in your brain just now. You said, okay, well, I'm going to take the total number of years, 4,860, and I'm going to divide that by the time of 1 half-life, 1,620. And that will give you the actual number of half-lives. But here to write it formulaically, oh, it's working. We write it as t to the 1/2. Then here's what you did. You said, okay, if I want to find the amount of time t, what I'm going to do is I'm going to take the amount that I started with, and because it's a half-life, I'm going to divide it by 2. But I'm going to divide it by 2 as many times as I have half-lives. So if I have 1 half-life, I'm going to divide it by 2 once. If I have 2 half-lives, I'm going to divide it by 2 twice. If I have 3 half-lives, I'm going to divide it by 2 3 times. In other words, I'm going to divide it by 2 to the n, like this. And this is what you did in your head. You took 8 grams, and you said, I'm going to divide that by 2 for as many half-lives as there are. And to find the number of half-lives, you did 4,860 years divided by 1,620 years. And when you did this in your head, you said that is equal to 3. So then you had 8 divided by 2 to the 3rd. And when you did 8 divided by 2 to the 3rd, that's 8 divided by 8. You got 1 gram. That is the McKellips way to do this problem. Let's take a look at the Saxon way to do this problem. I'm going to go ahead and pause the video really quick, erase all of this, and then we'll come back and do the Saxon problem. 1 second. Let me get this cleaned up. Okay, now here's the Saxon way to do this problem. You say this looks like exponential decay, so I'm going to use my exponential decay equation. And I'm going to say that the amount at time t is going to equal the amount that I started with times e to the kt. And when you start with k, you know that you have to find k, but for a half-life situation, I can tell you exactly what it is. First, you know that k is negative because this is exponential decay. And for half-lives, it's always going to equal negative natural log of 2 all over the half-life every single time. You could actually memorize that if you wanted to. That gives you a formula that looks like this. we say that the amount at time t is equal to the amount that you started with times e to the negative natural log of 2 all over the half-life. Now you could plug in numbers. The amount that you started with was 8.0 grams times e to the negative natural log of 2 all over 1,620 years. Like this. Oh gosh, I forgot my times t. I was like, where is my time actually? Oh, wow, that was embarrassing. Times, there we go. This is going to make everything nice and good and perfect. 4,860 years. And that, if you type it into your calculator, gives you 1.0 grams. Both of those ways are totally great. On a test, you could use either one. Go ahead and try both types on your homework tonight and see which one you like more. That is a little bit on half-lives and how to use half-lives to find the amount that's remaining. Now, I want to go back to this example that we looked at the beginning of class with these different emitters and what each of them gave you. So let me go ahead and pull up a little tab, and I'm going to put our data up here again. 1 second. Okay, here we go. This is our data from earlier. We saw that each of these have different half-lives. My alpha emitter has a half-life of 138 days. It's a little bit of polonium. Has a half-life of 138 days. My beta emitter has a half-life of 28.6 years. And my gamma emitter, which is a little bit of cobalt-60, has a half-life of 5.27 years. Now, here's what I want you to look at first. First, just look at my gamma emitter and my beta emitter. That's what I want you to look at first. Here's what I want you to see. Do you see how the half-life is actually showing you how fast this thing is decaying? So if you have a much shorter half-life, that means that thing is decaying much more rapidly. So my gamma emitter is decaying at a much faster pace, which means it'll make the Geiger counter light up a bunch more. Meanwhile, my beta emitter is decaying much slower, at a much slower pace. It's going to take it 28.6 years to get rid of half of that stuff. So it's decaying much slower. If it's decaying much slower, it's not going to light up the Geiger counter as much because it's taking longer for it to decay. If you looked at their graphs for each of them, gamma, let's go ahead and look. Gamma would be much steeper here than my beta. My beta would be a little bit more shallow. What that means is my gamma is giving off way more radiation than my beta is. And so you can see that you can actually look at the half-life and use the half-life to figure out, is that going to be emitting a lot of radiation or a little bit of radiation? But that's not the only thing that matters. Look at my alpha. My alpha has the shortest half-life of 138 days. So you would expect that my alpha emitter would cause this thing to go crazy. It's emitting, you would say it's decaying so rapidly fast that it should be shooting out little alpha particles like crazy. But my polonium isn't doing that. Why? See if you can figure it out. I'll give you a little hint. I have owned these samples for at least 3 years. If I've owned these samples for at least 3 years, how much of my polonium from my alpha emitter is still polonium? Not much. At this point, my polonium is mostly lead. There is very little polonium left in my sample because it has such a fast half-life. If you look at this little alpha emitter here, its graph is the steepest of all 3. But we're at like this point on the graph for this guy versus being at like this point on the graph for this guy and like this point on the graph for this guy. You can see that for this one, there's literally just not that much polonium left that's decaying. And so the amount that's reaching the Geiger counter, well, there's just very little left of it that's actually being radioactive. So you can see that the radioactivity or the Becquerel count for each of these depends on their half-life. But it also depends on how much is left, how much they've been around. Your half-life depends on how much stuff you have and how fast it's decaying. Your half-life tells you how fast it's decaying, and then the amount of stuff that you have, well, isn't that like in this situation, also kind of determined by the half-life, because I started with the same amount of all three, but this one decayed so rapidly that I have so little of it left. And that's the idea. That's why I got the Becquerel counts that I did for each of these three. Now, that is all for today. But before you go, can you please take a look at all the notes that we took, and can you please remind yourself of the following things? First, what is half-life? Why do we talk in terms of half-life? Why is that a useful way of talking? Second, why is all half-life exponential decay? Why are half-life situations exponential decay? Third, what are the two different ways that we learn to calculate half-life? And lastly, why does the Geiger counter go crazy for some samples and not for others? What factors matter? Go through each of those 4 questions, and that is all for today, folks. I hope you have a wonderful, wonderful rest of your day. Bye, good people.